Looks like it's start time, and I think you know this, but I will just say, obviously, the test is not today, and it is next Tuesday. Give you a little breathing room, but of course that means you're going to be more than ready for the test, right? You are got that whole extra weekend, so that way I can put some real hard problems on the test, right? No. I know. All right. Well, let's finish up this chapter then. I've got 4 more examples I'd like to do for you in chapter 26 here. And that'll put the end to our first 4, and we'll be ready for the exam. So, the exam coming up on Tuesday. Same as before, those the few of you who are in here who haven't had me before, it's 5 questions, and it'll just be 1 on each page, and you'll do the first one hopefully, turn the page, do the second, do the third, do the fourth, do the fifth, go back, check it, feel good, turn it in, and leave and have an extra hour in your day because you did it all in the first hour. Or maybe not, but somewhere along the line is that's all we do that day. So come in, take the test. If you're done early, fine, leave. If you aren't, and keep your eye on the clock, rushing to the very end. And obviously it covers these 4 chapters, chapters 23, 24, 25, and 26, okay? And so like I said, I'd like to do 4 more examples for you. Then we better get started in the next chapter. I don't want to do too much in the next chapter because I know your focus is obviously on what's coming up on the test. But because we did bump it, we do need to spend a little bit of time. And the stuff we do is, in this beginning chapter, is pretty straightforward. Nothing real tricky, more conceptual than mathematical, kind of a good stuff to do in terms of getting ready, but not really getting into some detailed math, which will come after the test. And actually, I don't even know if this next chapter has much complicated math. It's the chapters after that that we start to build up and get more complicated math here. So maybe that's some good news for you, that what's coming up will be a fairly straightforward, I don't want to say easy chapter, but certainly easier than the stuff you saw with Gauss's law and the stuff you're getting ready for in terms of the exam. Also getting ready for the exam, we got tomorrow, you got the MC, so take advantage of that, obviously study, come in with lots of questions. In addition to that, we got the Sunday review, and so Sunday 1 to 4, Don will be here and do the review for you, and we'll work on those, and then I guess Monday you got a chance for the last ditch questions. Come in and ask Don or me about the problems. But then I will see you again on Tuesday, and we'll take the exam. All right. Well, number 30 is the next one I have on my list, and I've done quite a few examples of different problems. In terms of how do you calculate the capacitance and some other problems we've been doing. But 30 also is like the one we just left off. It is a good one to do. It's got some little subtleties in it. 2 big things I want you to see here. But here's the circuitry here. It starts off with this, and it says, look at the circuit. All right, so I will draw the circuit up here for those of you who might not have it with you. It has this standard symbol we've been using for the power supply. And so there's our voltage. If you read down in the problem a little bit further, they say this is a 100-volt power supply. So maybe a lot of batteries hooked together to get our 100 volts. The new symbol we learned last time was this little metal connection. We called it S for switch, and then the wires head on up there. And so I thought I would take a moment today and say, okay, I should bring a switch. Here it is. So maybe the symbol looks pretty obvious to you, okay? That, if we were hooked this up, and we will do some hooking up, but not for this chapter as we get started into the next chapter. But this part of the circuit would look something like this. So we would have the rest of the circuit connected here, the rest here, and here's the metal here. Closed, right? Light goes on, light goes off. And so that literally is our connection. You can see why I jokingly had said that I usually don't bother to put a switch. If you want to switch, it's just, that there, connected, disconnected. Because literally it's doing the same thing. But this is a kind of our simplified switch. One little post putting up, okay? So it's what we call a single pole, single throw. It either goes on or it goes off. Some of our switches you'll see will get more complicated, but single pole, single throw switch. All right, so there's our switch, but the real part of the problem begins here, where the wires come in and are hooked to a spring before they go to the parallel plates of a capacitor. And they've got a spring on both sides here. Okay? And then they said that this is a distance d. So there's the figure. Let me keep reading here. It says, look at the circuit shown in figure 30. It consists of two identical parallel metal plates connected by identical metal springs to a 100-volt battery. When the switch is open, the plates are uncharged and are separated by a distance of 8 millimeters and has a capacitance of 2 microfarads. So in this particular configuration, the distance between them is 8 millimeters. The capacitance then comes out to be 2 microfarads. As I read the problem, it then says, when the switch is then closed, the distance between the plates decreases by a factor of 1/2. Okay, well maybe I should ask why. Why does it decrease? Yeah, and of course this ties a little bit of our mechanics. Aren't they hooked to a spring? Is there any force between those two plates? Yeah, where does it come from? Yeah, this is our electric field. So as this one closes, these electrons come off and they pile onto here. There's positives here, and so they are being pulled together here. And so if they were just two metal plates floating in outer space, they would have an acceleration and they would have opposite charges. They would come together. So in this case, they obviously don't actually completely come together because they pull on the springs. I suppose you might argue that if you actually turn this on, the charge would build up and it would pull in, and then the momentum would take them too far and the springs would pull them back, and then the electric field, and so they'd probably do something more complicated like that. They're not asking us to go that far into our mechanics, but I thought it would be a good problem because it does show our new material that we're learning this semester, as well as ties it in with a little bit of mechanics from our past chapters. And it's always nice to do a few that have those, so it always keeps that fresh in your mind and you gain more experience and hopefully learn it for the long term. But nonetheless here, that they are saying here as the 8 millimeters now gets decreased to 4 millimeters. That's what they're saying, okay? And what I want you to notice, and the reason I picked this, is there any changes to that capacitor? Yeah? Yeah, so the capacitance then is given by the area and the distance between them, and the material that is buried inside of it. And we don't even actually know if there's any material in there. I assume it's not. They don't show anything, and they do let it get closer together. So I'm just going to say it's, empty space here or just some air, and it moves a little closer together. But we do know this. We do know when this is 8 millimeters, before we even charge it, they say we get a capacitance then of 2 microfarads. And what I wanted you to see is it still going to be 2 microfarads now? Now it moves closer. Increase or decrease? Increase. By how much? Yeah, twice as much. So maybe I will put then new capacitance is at 4 microfarads. And so there's the first and important step. There's the physics of it to get you to realize, wait a minute, the capacitance will change. The capacitance does depend on the distance between them, as well as the area and the material between them. But in this case, what's changing is the distance between them. So there's a slight separation here, or change in the separation. They got closer together. And that's one of a couple of big keys here in this. It says, when the switch is closed, the distance between decreases by a factor of 1/2. A, how much charge then collects on the plate? Okay. Well, now I don't think that is too hard of a problem. This is, we did ones like this, right? We said what will happen is when you close this switches, the charges will come around here and they will build up. And we had this whole definition that capacitance is charge divided by its voltage. And the first part of this was to say this is a 4 microfarad capacitor now. It is no longer a 2 microfarad capacitor. And the second piece of the physics, again, I think you know, is that, well, it's going to build up until the voltage is what? Yeah, it's 100 volts. And so that whole reason more electrons won't come out of this battery is because this charged plate is repelling them. And it will repel them equally when this gets to 100 volts. So this is 100 volts, that's 100 volts. So this will build up to 100 volts. And so that was our 2 steps, and we learned this chapter. And so now I can then just solve for the Q. So once I write that out, then 100 times 4 is 400. So it's 400 and it's micro, and when I do a farad times a volt, I get a coulomb. So 400 microcoulombs of charge is what builds up on this plate. Okay? And so there's A. But then B goes on to say, so what is the spring constant? All right, well, how do I do that? Now, obviously, this is going to take us back a step, right, to our mechanics. And also tie it in with our electricity that we're learning now here. Okay, good. So I hope you remember Hooke's law, right? And Hooke's law says that the force you get from a spring is minus kx, right? Where x is that spring constant. So that's good. The minus sign I won't worry too much about. That just is telling me that the direction is opposite of the distance it moves here. But before I charge this plate up, that would be the natural length of the spring. And so as they came together, obviously closing up 4 millimeters, if I'm looking at just one of the springs, then how far did one of the springs stretch? Yeah, 2 millimeters, right? And so there's an important physical picture here to realize that, hey, this one is going to move in 2 millimeters, and this one is going to move in 2 millimeters, closing the gap of 4 millimeters. And so there's my x. How far did it move in? All right, 0.002 meters. Okay? So at least I have one of these 3 things. And of course, I'm asked to find K. So the other thing I need to know is the force. Well, here's where this chapter or this semester comes into play. How do I get the force, say, on this one plate? If my focus is on this spring, we just said the spring stretches 2 millimeters. But how do I get the force on this one? Okay, good. So the force must be the charge that is there times the electric field. Fair enough? All right, well, I'll start with the charge. I think I kind of know that one. How much charge is here? Okay, good. And one of the reasons I brought this up is, you know, what charge am I asking about here? Am I asking about the charge on this plate, both plates? Yeah, and as I look at this, I'm looking at what is the force on one plate. Let's call it the positive plate. What is the force on that one plate? Well, I would need the charge from that one plate multiplied by the electric field that is created by the other plate. Isn't that the way this works? Right? The charge placed in the presence of a field. The field is created by the other charges, and this charge is the other plate. Okay, well, I already did that, so I know this one. It was right here. So according to this force that is electric is going to be the same as the force from the spring. That's our equilibrium as it closes back in. And then I've got my 400 microcoulombs for my charge. What's my electric field? Glad I heard this. Sigma over epsilon, except it is a little off. Didn't we say it was sigma over epsilon between the plates? But why did we say it was sigma over epsilon? It's a combination of both plates. Is that what I want here? It's not. Why? Yeah, and so there's some little subtleties in here that, particularly right here, this is the electric field created by the other charge, right? And that's how we get the force between two objects. So the force between two objects is the charge that you place here times the electric field that is created from the other charges. So I wouldn't want just a sigma over epsilon. I would want that, right? I'd want it cut in half, because this is the field that is created from the negative plate, then multiplied by the charge that you put in the presence of that other plate. Really easy to overlook that factor of 2, right? All right, so now we're getting a little bit closer. Although I don't think they gave me any dimensions to this plate, right? I mean, I certainly got sigma. I mean, I got the charge, and if I had known the area of the plate, then I could get this, and I could probably finish the problem right now. But they don't, so I'm going to have to take a little bit more here. And so maybe I'll pause over here and say, well, let's draw the picture of any capacitor over here. If this is negative and this is positive, as I indicated, wouldn't there be an electric field between here? And so wouldn't the wouldn't the change in voltage, I'll just say voltage here, is minus the integral of E dot dr? And so in this case, the electric field is the entire electric field, right? The voltage includes both plates here. And so in this case, I want both plates. And so that little subtlety makes an important distinction here. But nonetheless, it's a total electric field for a distance of d. And then that would be the voltage between them. And I know this number. I know this number is 100, right? And I know, and I'm not even going to worry about the direction, so I'm just going to say absolute value here and drop that minus sign. And then the distance between them is that 0.004, right? And that's 4 meters. Okay? And so this sigma over epsilon becomes what? 100 over 0.004, 1,000, 1, 2, 3, makes a 4. 4 goes into 125,000 times. So I do know that number indirectly, right? Could even find, I guess, the area of the plate from that, because I do know the charge. All right, so if I take that and jump back over to here, I then have 400 microcoulombs of charge. I have a factor of 1/2. I have a factor of 25,000. Maybe I should watch my units here. I got volts over here, meters over here. So this is volts per meter. For that matter, I guess it's also newtons per coulomb, because it is an electric field, right? And so this is our traditional, and I say traditional, the one we learned first in terms of what are the units for an electric field. And we learned it in terms of force. But now we're dealing with electric field in terms of energy. So it's probably worth mentioning that another way of representing the unit for an electric field would be volts per meter. And so that's what I would have here. I would have volts per meter for there. Which hopefully works out really well, because if you then watch your units, I'll put my numbers here in just a second, but as far as the units go, I've got a coulomb, a volt, and a meter. All right, well, I'll leave the coulomb alone because the volt is a joule per coulomb. which means the coulombs cancel out and I got joules per meter. And a joule is a Newton times a meter. So when I divide by a meter, I come out with B newtons. Again, not a surprise, I hope. I am calculating force, and it should come out to be newtons. Okay? But take the time to look at these units, and you'll notice I've been looking at the units more so than I ever did for you in 121, because I think that it takes some getting used to working on these units. For many of you, most of you, you're working with volts and joules and newtons per coulomb or volts per meter. You know, all these are kind of new, but they do work out. Yeah. Back here? The factor of 1/2 is because the whole electric field is just this. Okay? But what I want to know when I calculate the force between two objects, if we go back to chapter 23, if you wanted to know the force on that charge, how do you get it? Well, you take that charge multiplied by what? The electric field that is created by that other charge. Right? So same thing here. I'm going to come back over here and I'm going to take the charge that's on the positive plate and multiply it by the field that's created by only one plate. Okay, and so that's where the half is, because half the field comes from one plate and the other half of the field comes from the other plate. Okay, so now that my units work out right, now I'll try my calculator here. So this is 400 times 10 to the negative 6. Times a half times a 25, 1, 2, 3,000, and oh, well, I guess we don't need a calculator for that, right? All right, 5. But there it is, 5. Yeah. All right, so there's 5. So now finishing the problem finally, Hooke's law, and the spring constant here then, is I've got 5 newtons of force divided by 0.002 meters, which again I guess is 5,000 newtons over 2 meters, which is 2,500 newtons per meter. Is that right? 5 newtons. Seems pretty big, but yeah. Unless you guys don't see a mistake, I'll go with it and say, okay, that's the numbers. All right, but again, I don't think that too many of the numbers were that complicated, as much as there was a lot of little physicsy stuff in here, right? There is, careful which electric field we're doing, how do you get the charge density in terms of voltage, coming back to our mechanics, knowing that the whole thing charges up to 100 volts. Those are all the pieces of the puzzle I wanted to go through and make you see. Let's try this one here. Here's something a little different too, something we hadn't directly done in any of the lecture part, but the material's there and it's, you know, one you hadn't quite seen. So I thought I would grab it and try this as another example. 49. 49 says the following. It says a 2 nanofarad capacitor, parallel plate capacitor, is charged to an initial potential difference of 100 volts and then isolated. Okay? And so maybe I'll just kind of draw a picture. So maybe it's a lot like the one we just have, where we had the little switch, we had a 100 volt supply, we hook up a little capacitor. This capacitor is 2 nano. Oh, nano. Really? Did I read nano? 2 nano. Okay. Which is, by the way, is probably more realistic. I was back there, you know, in my mind I was thinking, you know, okay, if I was going to build that one, I'd probably have these plates, I'd have these springs, 8 millimeters between them. I mean, it seems like everything's about set up right for this one, but there's no way I'm going to get microfarad, if you guys remember from the lab. Remember hooking this up? I mean, this was in the 150 picofarad range. So, I mean, that number there was unrealistic. Maybe that's why this bothers me. It's so high. Maybe it too is unrealistic because of the unrealistic numbers it did. So maybe I shouldn't be surprised that I get a number that's more than I expected, but because the capacitance was more than, I think, reality. This is probably more reality. This one's actually would be even smaller than this one at 2 nanofarads here, but it kind of depends on how much spacing is between them. But anyways, that's what it says, 2 nanofarads, charged to 100 volts. But in this case, they say it's charged up and it's isolated. And so what they mean by this is kind of like you watched me do with the light bulb. I close the switch, I charge it up, and I disconnect it. Okay? And so I thought I would bring this out here to kind of illustrate what they're doing here. They're doing something like this. I won't actually bother to charge it up. I won't even bother to do a switch. But my switch will just be this final connection. But if this was on and I did it, it would be something like that. There's kind of what they say. And I obviously, that would have to be set at 100 volts. All right? But here's the interesting part of it. It is then isolated. Okay? And so what they're saying then is once you have charged it, you now disconnect the power supply, the switches. And the thing to realize is now that's charged, right? There's pluses and minuses on there. Okay, so if I drew a secondary picture on this, I now have a bunch of negatives on this side and a bunch of positives on that side. So that's the first part, but I'll keep reading the second sentence. It says, now the dielectric material between the 2 plates is mica. Now I don't have mica, but I do have some vinyl there, so that's why I put that vinyl in there. It does have a dielectric material in there. And then it says, mica has a dielectric constant of 5. A, how much work is done to withdraw the mica sheet? In other words, if I come over here and pull this out, does it force back on me? Am I doing work to pull this out? Or does it just easily come out? Or does it shoot out on its own? It's sitting in here and the charges go phew, and I don't have to do anything. So does it want to come out or does it want to stay in? Well, you tell me. And so again, this is a problem that we hadn't quite done here, but maybe I'll draw the picture here. If I put the dielectric material in there, and I'll change colors here, if you remember our discussion on Tuesday about the dielectric constants K here, which they said is 5, okay. We did say this increased the capacitance. You measured it in lab. You saw me do it here in class, but how did the dielectric constant affect? How did the material affect it? Why did we end up with a higher capacitance? Do you remember all that? Do you remember what our argument was? What happened to the molecules in here? Maybe I should make it a little bit bigger so you can see. Here's the dielectric material. Here's the plate. We've got a bunch of negatives here, positives over here. And the real key to this problem is to go back to this microscopic view here. Why did we get a higher capacitance? Well, the answer was capacitance is charge per volt. And it wouldn't create as much voltage as you move charges from one plate to another once you had a material. Why not? In other words, the electric field was reduced. And it was reduced because we said in the material itself, the molecules will get elongated in this. And some of the negative will go to one side of the molecule, leaving the other side. So one side will be positive, one side will be negative. Way back in 23, we called that a dipole, right? We separate. We have what you might call an induced dipole here, a forced dipole. This thing is stretched out. And the consequence of that is the electric field that used to extend all the way through without any problems, now some of the electric field terminates on the surface of our material. And our electric field is essentially weaker. And that's what we said. It would be reduced by a factor of the dielectric constant. Okay? And so that's how we argued that the electric field would be weaker, therefore the voltage would be weaker, therefore the capacitance would be larger. Okay? And so that's what we argued. But now this problem goes one step further. Take it out. What happens as you try to take it out? Yeah, can you kind of see that it is going to take an effort on your part? You are going to have to apply work to get this material out. When you have it pulled out, say this far, you've got right here on this edge, you've got negatives from this plate, and you've got positives from this edge there. Aren't they pulling each other together? And so what you end up having to do is work. You are trying to pull this out of here, and nature's trying to pull it back in. And so as you pull it out, you are doing work. And that's what this problem is all about. How much work would you have to do? You can't just freely take it out of there. It will create work. And hopefully that makes sense, because when you pull it out, what will happen to the electric field when this material is gone? Won't it increase? Wouldn't that mean it has more energy? Where's it going to get that energy? From you pulling it out. It should bother you if it didn't require any work on your part to take it out. Because all of a sudden now, just going to pull it out. And all of a sudden there's more electric field in there, more energy.
Why would that be bad? That'd be great.
Well, okay. In terms of the world's energy needs, that would be great. In terms of our current understanding of science, it should bother you because it's a violation of conservation of energy. But you're right. If you could find such a thing, you would have an instant Nobel Prize, I'm sure, right? You have just turned over one of the fundamental rules of science. You've discovered some other rule besides the Nobel Prize, which would already get you, what, is it $2 million now for the Nobel Prize? It would probably get you billions of dollars in terms of all kinds of energy situations. And of course, you would remember us City College people and donate back to the college. And yes, don't forget, I like red Ferraris. Yeah, that's right. So you can keep your first billion, but after that, donate back to the school. All right, so anyways, I wanted to set this up because again, this one too, and all the ones I picked here, I think got a lot of physics-y stuff. Not so much some of the math here, but the physics, the physical picture. And if you don't see the physical picture, you often don't know where to begin here. And so there is the work that is being done. In fact, that's how I'll calculate it. Now that I say it's going to take some work, which you will take your mechanical work, if you will, and create electrical energy inside of there. And so let's use that information, which really, I guess, brings us back to our Physics 121 again. We learned that work is the negative of the change in potential. And I'll put a little sub E here because I'm talking about an electrical energy. When we did a lot of this in Physics 121, we did it in terms of gravitational energy or spring potential energy. But now we're just going to carry this forward here and say, all right, here is the work being done minus, and I'll just take the final energy minus the initial energy, right? And so now I have turned the problem into one that I'm not worrying about the forces and doing an integral like work, but I've turned it in terms of energy. Energy stored in a capacitor. We know that equation. In fact, we saw 3 of them. Maybe I'll put them over here on the side. But how do you calculate the energy in a capacitor? I guess that was 1. That was 2. And that was 3. Right? And so we said they were all the same. Our key to the problem would be doing one that should say, all right, how do we calculate it? Well, it kind of depends on what you know. For example, when I start off, before I pull it out, so what I will call the initial potential energy, what do I know? Well, don't I know that this initial one gets charged to 100 volts? Right? And I know its capacitance. So if I was calculating this, I probably would start off and write this as 1/2 times 2 nanofarads charged up to a voltage of 100 volts. Fair enough? So that's what this starts at. But here's another little important piece of the physics. I now pull the piece of mica out. I know the energy goes up, but what changed? Anything? So, okay, so did the dielectric constant change here when I pull it out? Did the capacitance change? Yeah, so I guess over here on this step, and maybe I didn't leave myself enough room, maybe I'll put it over here. But when I go to calculate the final energy, I got to realize there's a new capacitance. Now that won't be too hard to solve, I don't think, because they told me that the dielectric constant of the mica is a 5. So what is that going to do when I pull it out? What is going to be what I might call the new capacitance? I mean, it was 2 nanofarads, right? What is it going to be now? Is it going to change by a factor of 5? An increase or decrease? Yeah, it's a decrease, right? So if it was 2, and maybe I should go back and check. When they said 2, did they mean it with the mica in there? The 2 nanofarads, 100 volt, then isolated. And yeah, it says there is a dielectric material between the plates called mica, which has a dielectric constant of 5. So I think they clearly mean that this is the capacitance with the mica in there. So when you pull it out, you're going to end up dividing that by 5. So that's my new capacitance. But here's really the other part I wanted you to see. I think this is the hardest part of the problem. Anything else change? Okay, you said the electric field changes. Agreed. But what consequence does that have on voltage, charge, and current, capacitance? Or maybe I should ask it the other way. Did the voltage change? Did the charge change? Is there still 100 volts on this? No. And if you miss that, that's going to make this problem really hard. Where's the voltage created from again? Isn't it the electric field between them? Didn't you just tell me as you pull it out, the electric field got stronger? Right? And so isn't this voltage going to go up? In fact, it's this increase in voltage which gives it more energy. We got more energy, got more voltage because I did work on it. I pulled this out. Now there's different ways we can approach that, but I think the easiest one is conservation of charge. What do you know about the charge on those plates? It stays the same, right? When I pull this out, I'm not putting more charge on. I'm not taking anything off. The charge on there is the same. So I would suggest then, when it comes to calculating the final energy, we don't use the 1/2 CV squared. Because I really don't know what the new voltage is, but I do know the charge remained the same here. And so I think this might be a better option into finding out what the energy is after I pull it out here. And so I would put a 1/2 Q squared over C. And before I can put any numbers in there, I probably need to also come back to this and say, okay, so what is the charge on there? I hadn't even done that. But since capacitance is then charge over the voltage, and this is 2 nano, and this is 100, clearly the charge on this plate is 2 times 10 to the minus 7, right? And so that's how much charge is on that plate. So therefore, when I come over here and I go 1/2, and then I can go 2 times 10 to the minus 7 squared over this new capacitance, which is 2 times 10 to the negative 9th divided by 5, I've got something I can work with. So the original capacitance and the original voltage gives me my initial energy. And so we can have something to talk about. Let's not try to do that in one calculation. Let's break it into 2 steps. This first one would be 1/2 times 2 times 10 to the negative 7 squared divided by 2 times 10 to the negative 9, and then this gets flipped up to the top as a 5. And so if I've done my math right, this is 5 times 10 to the minus 5 joules of energy. That's the final amount of energy. Whereas this one over here looks like, maybe I can do this one without a calculator. The 1/2 and the 2 go away. That's 10 to the 4th. So 10 to the 4th, that's 10 to the minus 5. So that's 1 times 10 to the minus 5, right? And so there is my change in energy. Minus 4 times 10 to the minus 5 joules. Okay, and so that's how I'm going to get the work done on here. So again, kind of a neat problem, a little different than anything we've done, except like I said, I think you can kind of work through that by looking at the physics picture. And maybe I should make a comment about the negative sign. If the negative sign bothers you, remember this is the change in energy on the capacitor. So this is the work the capacitor did. So in other words, I have to do positive work, right? So if the question is what do I have to do, so the work done by me is the opposite of what is happening on the capacitor. So there's my positive work, the positive work. It's going to take an effort. This is how much work I do, which is why I gave it more energy. I did this much work. And that capacitor went from a 1 times 10 to the minus 5 up to a 5 times 10 to the minus 5. Because I did 4 times 10 to the minus 5. It got my energy, conservation of energy.
I was wondering, it seems like it would get harder like the closer you get to pulling the material out. The charges like chase each other and build up like towards the tip. And does that get is it at a place?
It might a little bit, but first of all, so let me answer it in 2 parts. Maybe let's talk about what it might start to do, okay? And I think your visual picture is good, but it's also missing something. So it's going to do that kind of. So we'll talk about that. But the other side of this is, again, everything we've done has been this idealized infinite plate capacitor, charges uniformly spread out. And so, yes, I would agree that all of our calculations are what you might call first order, or what I'll call first year approximations. Gives us something to start about. Gives us something to talk about next year. Well, I guess you guys won't be talking with me. So you guys will talk about with your professors at UCSB or wherever you go, right? It's like you'll be talking about more exact detail. But so this would be our first model, if you will, the first one. And then the more detailed will be a smaller group of you, because many of you will go into areas that aren't connected to this. I would assume all you electrical engineers would be talking about this, while you mechanical engineers would not be talking about the next step. I would be my guess here, yeah.
Does that mean if you had capacitors separated by air, and you held a piece of that?
Yes, it would. Yes, it would. Now, it's not much of a suck, if you will, because look at that change in energy. It's really small. Okay? And so that energy, which if we wanted to translate that into a force, would certainly not be enough if to lift the weight of the material. So if I were to place it here, I highly doubt it would draw it in. I would think that the weight would pull it down.
Just put more bolts across it.
Okay, at some point, yeah.
So you could make a magnet out of something that isn't
I wouldn't call it a magnet in any way,
effectively.
but it's essentially like, yes. But without doing any numbers, my suspicion is the voltage would be so much that you would get arcing. Remember, there's an upper limit to our dielectric. We would get arcing. We would get sparks across there long before we were going to lift the weight of it. I might get enough that if this was resting on a really slick surface, so very little friction, to pull it in. And I can see that happening because I'm not lifting the weight of the material. I'm just sliding across a low frictional surface. So then, yeah. Then I can see that. I don't know how much I should say, but I have seen recently some just new experimental, fascinating, where they will use then charges that come on here to do essentially what you're saying here, but maybe the charges will go on and off at a fast rate, so the charges kind of make a wave across the material, which then deforms this in a wave material. And for those of you who took optics then, if you shine a laser beam, the index would change in a pattern. And you could control and steer the beam based upon the electronics. So no moving parts. It's not like when you go to the grocery store and you see that laser beam sweep across because of the spinning mirror. None of that. We can sweep it. We don't have a CD player where the little laser head has to move along a track only to break someday. It sweeps along as the voltage changes. These could translate from maybe instead of light waves, but it could be acoustic, right? And so now I can have tiny speakers that could now fit something kind of flat. And if it wasn't actually for these piezoelectric speakers, and I'm talking about stuff beyond the piezoelectric, but even these piezoelectric, you would never have cell phones as flat as we do today, and the headphones as flat as we do today. That's a big step in terms of controlling the shape of the material through the strength of the electric field. Yeah, and so a lot of high-tech stuff going on in that sense. But back to yours. I think in your mind you're kind of imagining everything get pulled down here, but don't forget that they don't want to go down here because then they do want to get pulled across there. So I don't think there's going to be as much accumulation down here on this corner as your mental picture had it. They're going to be left to be drawn back up here. So it's not quite, I think, what you were thinking in your mind. Well, all right. Well, I hope those... oh, wait, there's a part B to this. What is the potential difference now across the capacitor now that it's withdrawn? Okay, so part B is saying, well, now that you've done that, what is the voltage? Okay, and I suppose we have a couple of ways of attacking this now. Maybe the easiest way is to realize that as we pulled it out, the electric field just increased by a factor of 5, didn't it? I mean, that's what this dielectric constant meant. The dielectric constant means when you put it in here, the electric field is reduced by a factor of 5. So now we've got the electric field increased by a factor of 5. And since the simplest case, the voltage between two parallel plates is E times the distance, if you increase this by a factor of 5, what's going to happen to the voltage? It's going to increase by a factor of 5. And like I said, that was really the key to this problem, to realize when you pull it out, what didn't change. And it was charge in this case. Some of the ones you have on the homework leave the power supply connected. And then pull it out. So what remains the same there? See, the voltage, which means in this case the charges are going to have to go back into the power supply. And so all this work I am doing ends up recharging my power supply, not making the voltage higher. So you got to look at what's going on, what doesn't change, which is really everything we do in science, right? I mean, isn't that why we had conservation of momentum? We looked at what didn't change before and after the collision. Conservation of energy. What didn't change? Conservation of angular momentum. What didn't change? And so these become the starting points. These become the powerful tool. What do we know is not going to change? So with the power supply disconnected, it became a very different problem than if the power supply was connected. Anyways, I guess the answer then is 500 volts. It would go up by a factor of 5. So if we already had it at 100 volts, now we're up to 500 volts. Alrighty. Well, if and I'm tempted to even do it. I mean, couldn't I do it here too? Couldn't I set this new energy equal to 1/2 CV squared? And if you do, you're going to get 500 volts. Okay. Another one I put here on the list is 58. Again, kind of a little different problem. More of practical on the engineering side here. So okay, we're gonna build something here. This happens to be an audio amplifier. And so the last stage, so here's my amp. The last part of this amp has a little capacitor in it. Before that goes off to my speaker. And so as I send charges onto that capacitor, it's going to charge and discharge, which sends the charging and discharging to the little speaker. And as the current flows through there, the little diaphragm moves back and forth and makes my sound wave. So there's the simplest way of explaining, how does the speaker work and what is the kind of the last part of my amplifier. But there is a little capacitor on there. And I shouldn't say little. This is the stuff that usually blows out, because this is the last part. This is where the most power is. This is what you're going to be charging and discharging, and probably quite a bit, in order for it to go through the wires and make the paper diaphragm move here. And that's what this problem is getting at. It says to repair a power supply for a stereo amplifier, the electronic, actually I guess they say power supply, not the final stage, but somewhere it says here the technician needs a 100 microfarad capacitor capable of withstanding a potential voltage difference of 90 volts. Now, withstanding up to 90 volts, why can't it go higher than that? Why would a capacitor have a limit to it? Right, so we're back to this. You put some material in between here, or even if there's no material, at some point the electric field gets so strong that if we come back to a picture of these dielectrics here, and we are pulling the molecule, we are elongating it here. This plate's negative and this plate's positive. At some point you will rip that molecule apart. And we called that its dielectric strength, right? We said there was a limit to that. And that's kind of what we did at the very end of the lecture last time. All right, so every capacitor then is going to have an upper limit. And when we mentioned the ones that I used, that really big 1 farad one had such a small voltage, 5.5 volts, because the plates were so close, which gave it the large capacitance. Okay, so that's what we need. But here's what happens: we go immediately to our stock room, and we find out that we have a box of 100 microfarads. But they can only withstand a voltage of 50 volts. What do we do? Besides go back to the store. So again, the idea is we want a capacitor, but can't we put multiple capacitors together and get the equivalent? Yes, right? And that's what we're going to do here. So we really want this. We really want one capacitor that has a capacitance of 100 microfarads, if I read this right. But it can take up to 90 volts. That's what I'd really like. The problem is I have something close to that. I have a box, and so if I grab 1 microfarad capacitor, it can only handle 50 volts. So if I put that in, it just gets fried. That's not going to do. Answer? Yeah, I heard somebody say series. Okay, fine. So I will put a second one in series. Now the advantage of that is if you put 90 volts between these two, isn't there only 45 volts across each of them individually? Right? Oh, good. That's less than 50. They won't blow. Well, wait a minute. What is this equivalent to? You put 2 100s in series, what's its equivalent to? Is it still 100? No. So this is not going to cut it. You go 1 over 100 plus 1 over 100 equals 1 over the equivalent. That's 2 over 100 is equal to the equivalence. That means the equivalence is 100 divided by 2. That's 50. All right, so now we don't blow it because it has the correct amount of voltage, but now we don't have enough capacitance. So now what do we do? All right, good. So you guys see it, and that's all I wanted to go through. So if I were to do this with a second one in parallel, if you will, then take that and do this, which is a lot of wiring to make it look probably something more like this. Well, I guess either one would work, huh? Like that. But then this, as you said, would only have about 45 across it, so that's good. And these two together would be the equivalent of a 50 microfarad, and these two together would be equivalent of a 50 micro. But since these two are in parallel, then this is really equivalent to 100 microfarad. So there it is. 4 capacitors hook like this, or hook like that, right? Would then be equivalent to that one capacitor, 100 microfarads, that can handle the 100 volts. And so now it's going to work. So I'll just hook up 4 in this pattern. So that's what I was kind of after there, is could you kind of put all this together and do the equivalence of all of that. Well, one last one, and our hour will be up, and then we should go on and get started with the conceptual part of the next material as we go past capacitors and into current and resistors here. But 45 is also a good one because it does gonna, make you think about the things we did in class, kind of a different type of problem, one we haven't seen before here. 45 says the following. It says that the inner conductor of a coaxial cable has a radius of 0.8 millimeters, and the outer conductor's inner radius is 3 millimeters. Well, maybe I'll stop there and draw a little picture, because there is our coaxial cable. So here is the center conductor. Here then is my outer one. And so now I think you're getting the, if I say coaxial cable, you know what we're talking about. So I passed them out twice there so you could kind of look at them, right? And so this is my coaxial cable. Oh, I'll put the numbers on the board here. What did it say? It said the radius of the inner conductor is 0.8 millimeters. So here is 0.8 millimeters. And then here, I believe it said 3 millimeters. I'll go back and read this. It's 45. The outer conductor's inner radius is 3 millimeters. Now the space between the conductors is filled with polyurethane, which has a dielectric constant of 2.3 and a dielectric strength of 18 million volts per meter. All right, so what we mean by that, of course, is this dielectric constant, kappa, is 2.3, and its dielectric strength, and we don't really have a symbol for that, do we? And I'm trying to think of a traditional symbol. I don't think I have one here, so I'll just put 18 million volts per meter, and I'll just put DS here. How's that for dielectric strength, okay? But that's the largest electric field. I'll ask it again. Why is there an upper limit? What will happen if you exceed that limit? Yeah, what's it saying here is it's going to spark, it's going to tear apart, it's going to burn up the material inside there. Oh, shoot, I said I would bring one, huh? All right, well, next time. Oh, next time you have a test. Okay, a week from today, try to remind me. That'll be your job, Don. Remind me to get a little capacitor. Because, well, like I said, some of these are kind of neat when the material burns up. Most of the capacitors, they just burn up and they just turn, and you can't really see it because it's inside, but it just turns kind of flaky black inside. Not a big deal. But the ones that break apart and turn into a gas then are building up pressure. And then the whole thing just, you know, pops there. So, and like I said, they're getting really hard to find. In the old days, they were easy to find. I mean, everyone just did that. But now they've got these fancier materials that were designed that so people don't blow up their electronics and get themselves hurt. And so they've switched to all these non-explosive ones. So, but it's still neat to see here, and when it comes apart. All right, but that's the, like I said, the physics of it, of what is going to happen. So the bottom line is we never want the electric field anywhere between these two conductors to exceed that. If it exceeds that anywhere in there, that part is going to, you know, be destroyed. Okay? And so that's where the rest of this problem goes here. It says, what is the maximum potential difference that you can put on this cable? So obviously, if we hook this cable up like we're doing in our labs with our BNC connector, there's the round connector, we hook it on. If we set it to 5 volts, that's going to make an electric field that's probably a lot smaller than this, and everything's good. We could probably turn it up to 100 volts, maybe even 1,000 volts. But at some point, we will have too strong of a field. And that's what this is asking. With these dimensions, with this polyurethane, how high can we set that voltage before we destroy it? Okay? Well, the reason this makes a good problem, and I'm sure your author puts it as magenta, is, do you have a uniform field in here? What does the electric field look like inside this coaxial cable? Do you remember? If you start putting charges on the inner conductor, which you've taken them away from the outer conductor, doesn't the electric field look radial? Is that a uniform electric field? Right? Those lines are really close together by the inner conductor, right? So if you didn't catch this back when we do Gauss's law, let's do Gauss's law again, because I can get the formula for the electric field, and what you'll see is it does change depending on where you are. And where is the electric field the strongest? Right on the surface of that inner conductor, and that's what you need to know. In other words, the limiting factor here is we would have to keep the voltage low enough so that the electric field right along this inner conductor does not exceed that. Now everything else is going to be lower than that. But if you turn this voltage up too much, at some point the electric field will exceed this, and it will do that first right on the surface of the conductor. And that's where you're going to destroy your material. That's where you're going to destroy your conductor. And that's a key step here. So I'm going to come back a couple of chapters and do Gauss's law. Do I have a green one here? I've been doing Gauss's law for whatever reason in the green. So let me draw a Gaussian surface. Only because I do not know the formula for the electric field from this cylinder. You may have already memorized it. I would say if that works best for you, then do it. But I'd say just work it out. Work it out for the case you're going to be working on. And this is the case I'm going to be working on. So I will apply Gauss's law here real quick. So E dot dA equals to the charge inside over epsilon naught. That's the fundamental physics. That can explain how I can get the electric field. I get the electric field by three ways we learned in chapters 23, 24, and 25. This is 24. This is Gauss's law. And so when I draw a Gaussian surface that has a radius of r and has a length of L, I will argue that the electric field is the same along that wrapped around part, that face. I would say that the surface area is 2 pi r times L. And so there is our real quick Gaussian integral, the flux along that rounded part. Top and bottom, the flux is 0, so I won't even put that on here. Charge inside, well, that is the charge density. How much charge do you have along that inner conductor multiplied by its length? Cross off the length and we get this same formula that we've seen a number of times, but this is the electric field then inside this geometric shape. It is not uniform. The parallel plates gave us a nice uniform. That's why we use this one so much. We see it a lot in the lab. We do our calculations a lot. It's the easy one. This one is also very convenient. It's not quite as uniform in the sense that it has this R in it. But now you can see, as you go to calculate the electric field, where would you get the largest field when R is the smallest, right? And that's going to be right up against this surface again. So again, it matches my picture. That where I need to be careful here is I don't want this electric field to exceed that value, right? So we'll come back to that, but the question is, what is the potential? So how do I calculate the potential between these two surfaces, right? I am going to integrate that electric field from one surface to another. So I've got this integral of, and that's why I need the electric field, 1 over 2 pi epsilon naught, lambda over r dr, and I will just go straight out from one surface out to another. I won't even decide which way I'll go. I can go from inner to outer, and it's either 0 or 180, and whatever I get here, it's plus or minus. Whatever I get here, I'll ignore, it's plus or minus. So not worrying about pluses or minuses. Obviously, you know, one direction is higher than the other, depending on which way you charge them, but just ignoring all the pluses and minuses, I get lambda over 2 pi epsilon naught ln of r evaluated from this 0.8 times 10 to the minus 3 out to 3 times 10 to the minus 3. Or lambda over 2 pi epsilon naught ln of 3 over 0.8, and then the times 10 to the minus 3 is going to cancel off. So that's going to be the voltage. So that's really what I'm after right there, right? That would be the voltage. And hopefully it doesn't surprise you that the voltage depends on the inner and outer radius, and it also depends on how much charge you've put there. Now, isn't there going to be a maximum charge? Well, that's what this is saying, right? There is a maximum charge because there is a maximum field. And so I can figure that out from here and put it into there and then find out this maximum voltage. Yeah.
Can I do outer minus inner radius?
Sure.
Will you get the same answer?
Well, in terms of absolute value, yes. Right? Because if I go if I go ln of R evaluated from R1 to R2, I get ln of R2 minus ln of R1, which is the same as ln of R2 over R1, right? Which is the same as ln of R1 over R2 raised to a negative 1 power. Which is the same as negative ln of R1 minus R2. Which is the same as the negative of ln of R evaluated from 2 to 1. And so 2 to 1 is the same as, or excuse me, 1 to 2 is the same as 2 to 1, except for the minus sign. And as I said, I'm just going to talk about the voltage. So one can be higher than the other. It doesn't matter which way, and I'm not paying any attention to which way it is. The way I have it set in my picture, I obviously have the center one at a higher voltage. So if I go from the inner one to the outer one, I should get a negative number. And so I'm just kind of overlooking the negative one just to find out what is the highest magnitude of the voltage between one conductor and another. So back to this then, what that tells me then is this largest electric field, which is 18 million volts per meter, would occur at a radius of, wait. Whoa. I need to be careful here. I almost skipped over something very important here. What's this?
Permittivity of free space.
Yeah, so what have I just calculated back here? Okay, so this would be the electric field with what between them? Right? With air? Now, do a vacuum, air, kind of same thing, okay? But I don't have that in here. So before I go too far and fill this in, I need to realize that. Wait a minute, this was the electric field for air. What would be different now that we filled it with polyurethane? Yeah, it would be reduced by that dielectric constant, right? Okay, so really I should have this, that the electric field is 1 over 2 pi epsilon reduced by a factor of kappa L over R. Okay, there's my electric field. Yeah.
You can make it a K equal to epsilon, permittivity of material over epsilon naught, right? And then just plug in epsilon instead of epsilon naught.
Oh, yeah, and that's what you asked me in the lab, so yeah. Same thing. Now, there is a subtlety here. It kind of depends on what they mean by how they measured this. And I'm kind of concerned about that. But in the interest of time, maybe I'll just... Because when they measured this, did they mean this is equivalent to no material, or is this with the material when it broke down? I mean, what did they mean by this number? Shoot. And
with the material?
You think it's with the material? Okay, I'm thinking 2, so I'm going to go with this. All right, and I'm going to put that K there. That's where I started, so I'm going to keep going. Yeah.
The dielectric strength is measured in volts per meter. Why wouldn't that just be a value of the electric field?
It is the value of the electric field.
So why do we have to calculate the voltage?
Why do we have to have what?
Why do we have to calculate the voltage?
Because that's the question. What's the voltage? See, what we know is the limit of the electric field. That's the material strength of it. So if you're the electrical engineer, you've got to go this step. You've got to say, okay, here we're going to do. We're going to build a coaxial cable. We're going to fill it with polyurethane. We are then going to type on the edge of it, do not exceed this voltage. And how much is that? So you're going to have to calculate from what do we know about the dielectric strength of the polyurethane to the voltage given the dimensions of our cable that we're building. That's what we want. We want to make sure it's well printed across the side. Okay? So that's kind of the real world application of what's going on here. You're not going to put on the, don't exceed this electric field. That's not going to help anybody. Somebody who's hooking this up is hooking it up to a voltage, and they want to know what is the maximum voltage I can get. So they want that typed on the side. They want you to do this calculation when you manufacture it and write it on the side. Do not exceed this voltage. Because they couldn't do it unless they knew the inside dimensions and what the material was. Okay? But all that is put together in terms of the voltage. All right, so with all that said here, this would be the electric field in free space. This is reduced, and this is why the K shows up here, right? It's reduced a little bit. And again, I do not want that electric field to ever go over that value. So keeping this in mind, I'm going to say 18 million volts per meter at a radius of 0.8 millimeters, that would really tell me the strongest charge density I should ever have. Given this radius and the limitation of that material, this is the largest charge density I should have. So lambda would be, okay, thank you, forgot the K again. Would be 2 pi epsilon kappa, by the way. I'm bad at that too, but it's really kappa. So we should call it kappa, not K. All right, kappa times 0.8 times 10 to the negative 3 times 18 times 10 to the 6th equals. Okay? So that step there is really what I was after in this whole problem and why I picked it. It gives us a way to calculate the maximum charge. Now once I know that, I can now come over to here and say, well, that's going to give me the maximum voltage. That maximum charge is what gives me up to the maximum electric field, and that's where it breaks down. So I can now put in my lambda. And so my lambda is the 2 pi epsilon 2 pi epsilon kappa 0.8 times 10 to the minus 3, 18 million. So there's that. I've got the ln of 3 over 0.8. I've got another 2 pi epsilon here. Those go away. And now I can finally put it into my calculator and say, what is this maximum voltage? The kappa was 2.3, so 2.3 times 0.8 times 10 to the negative 3 times 18 million times natural log of 3 divided by 0.8, all of that coming out to be roughly 43,000 volts here.
Why does the kappa not cancel? Shouldn't we have kappa in our voltage number?
No, it's only going to show up once. The voltage is the strength of the electric field. Right? So I have the at least I hope I'm saying that. Yeah, so this would represent the electric field with the material in it. And that's what I did here, right? I gave me the maximum electric field with...
Why did we not have kappa in that table right there?
This one?
Below that.
Oh.
The kappa should cancel on you.
Maybe did I skip it twice then?
Well, yeah, because you're supposed to have the kappa in
Pull it out.
Oh. Yeah, now I regret not putting it in earlier, but I think you're right. So if I'm going to place it there for the electric field, I need to do it. Okay, yeah, all right, so then it's less by whatever I said, 2.3, and yeah, okay. Okay, good, I like that. I need to give that one some more thought too. But in the interest of time, I'm going to say, okay, you got. I hope you got the idea of that. Let's change gears now. Let's say, all right, done with that chapter. You've seen a lot of examples. Got a test coming up. And we postponed the test a little bit, purposely to give us a little more time to let it sink in. But now let's look at this next step here.
Does this mean we're not doing any electric torque or electric dipole from the
Oh, good point. Yeah, the yes. Yeah, the very last section of chapter 26, yeah, goes into the torque on an electric dipole. And we're going to revisit that a little bit later when we get to magnetism. So, yeah, so not on the test. Yeah. So, right. All right. I forgot that little section was in there. Okay, so what's next here in chapter 27? Okay. Well, probably the best way I can get started into 27 is kind of show you how it's a continuation of what we just did. Let me put up here what we just did. What we've been doing was something like this. If I took a power supply, maybe 6 volts, and maybe even just take a little switch here, S, and hook it to a capacitor, C, and kind of hook it around there. Here's what we've been saying for the last week and a week and a half here. We're saying, look, if you come along and you close that switch, little tiny electrons are going to come out here. And they're going to start building up. Then what we said is the first one will come off here, chase off a little electron, send it around, and then a second one, then a third one, then a fourth one, and then eventually this stops, right? This stops because the electric field that is building up in here gets to the point that it has the same strength as this one. And that was our argument, that this would build up to 6 volts. Okay. But here's what we're going to change. What if we don't give it a chance to build up? What if instead we just hook a wire like that? What happens here? Yeah, it sends another and another and another and another and another and another, and it just keeps going until, I suppose, we run out of energy here. If this is a battery, this would eventually run out, right? Now that could be a lot of electrons, so let me change my picture a little bit. Let me make my wire a little fatter. At least most of the wire a little fatter. What do you think might happen right there in that kind of little narrow spot there? Okay, so these little electrons, and so here's what's different. When I close this switch, these little electrons are going to go along here, and they're going to get what you might call bottlenecked in there. They're going to try to get through there, but there's going to be some resistance, right? Some of you recognize the word. Some of you saw it in lab. Some of you have circuits. The rest of you have it today. But there's going to be some opposition for this to get in there. And you can kind of see then that as they kind of clump together, they're getting real tight. So what do you think kind of happens in there with the electric field? It builds up really strong too, right? And so there again, you get an electric field until you get kind of a balance going on here. I would still say you get 6 volts here. It's kind of a different scenario though. It's not a 6 volts because there's an electric field that is built up in the empty space between two conductors. It is a 6 volts because the electric field that is in the little tiny narrow part of this wire is created by all these electrons. And interesting enough then, won't they squeeze through? I mean, if this is like a freeway situation where you had 3 lanes and 2 of those 3 lanes are now blocked because of an accident, all those cars are going to try to squeeze in there, right? And everything's going to be going real kind of slow through there compared to when it was open and all 3 lanes were going, right? And so there is a bottleneck, if you will. There is some opposition, what we're going to call some resistance for those to get through. But nonetheless, they continue to go through, don't they? And so it goes through, and it goes through, and it goes through. And so doesn't this just keep going on? It never builds up to a full charges and stop. Fair enough? And that's the big difference. Because this part, and the time we have together, only 40 minutes here, I want to introduce you to 2 words. The concept of current and the concept of resistance. And as far as doing calculations and whatnot, we'll build up to that after we have the test. But just this basic concept, and if time allowed, maybe we'll do one simple calculation or something in one simple formula. But I'm hoping I at least lead to some kind of relationship, which is Ohm's law here, and that's what our lab is on this week. But this current is where I want to get started. What is current? And probably the easiest way to kind of define it here is to say, the current is electrical charges in motion. So before we got to this chapter, didn't we have current here? Weren't charges moving? Now granted, it was only at first. So you first closed the switch and maybe within the first microsecond you had charges. But after that, did you have any charges moving? No. So that's why we did not even use the word current. We didn't much about it. We just said, look, they're going to move, and we just left it alone. We didn't even give it a word, but now they're going to move, and they're going to be continuing to move here. And so moving charges really is our definition of current. I think your author does a good job in his first picture here. He says, look, it's not the most glamorous picture, but if you could shrink down on a microscopic level, okay, and you could pick some kind of wire, and so this is supposed to be the cross-section of a wire, and you've got some charges. Now the only thing that I don't like about this picture is it's showing positive, but on the other hand, that's going to be a good thing in a second here. Because in this wire, is it the positives that are moving around? No, okay, so keep that in the back of your mind, and so more on that in just a second here. But let's just say they are for a moment. Here's what your author is trying to say. Current is really this movement of charges. And so I take a little wire like this one here, and I cut it in half. And if I could see these things going across here, which it looks like 3 just went through and 2 more are about to come through here, the definition of current is labeled with an I, and so that's the symbol we will use. So here is the symbol I. Okay. The current really is the movement of these charges. Now, of course, it gets a little more complicated than that, because don't we have both positives and negatives moving? See, this simple picture only shows positive. Let me change it to another picture that your author has. I think it's picture 4 here. He kind of shows 4 different scenarios. An A, a B, a C, and a D. And they can happen in different cases, but let me jump right to D. This is probably the more realistic one for us, because if we take these metal wires, what are the things that keep moving? Oh yeah, these electrons here. And so I would say, okay, this is the picture we would have. We would have a bunch of negatives going in one direction, as opposed to positives going in one direction, right? Or positives and negatives. But I do want you to notice A and C for a moment. Did you notice that the positives and negatives would, of course, move in opposite directions? Right? I mean, come back to this picture. That's what this whole thing is saying. I keep talking about the negatives here, and so I'll put a little E with a minus, but these negatives come out of the lower potential and they move around to the higher potential. Because isn't that lower potential energy? Right? Wasn't that our whole argument of dealing with electric potential? Electric potential, when you measure it from high to low, and so I call this the high side and this the low side. Positives would want to go to lower potential. Negatives would want to go to higher potential. Each of them is going to lower potential energy. Each of them is losing electrical energy and making, usually in this case, like heat or light or a kinetic motion as a motor spins. I mean, we're using electricity to do something with.
Why do they keep saying the positive charges are negative?
Ah, hold on with that question. Good. And I do want to answer that.
Like, why not just explain it in terms of electrons?
You could have either way. But mathematically, it is kind of nice to talk about positives. You'll see that in just a second. So, but before I get to any math, okay, just that concept, what is current? Current is moving charges. So do I have current here? Yes. 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 Anytime you have moving charges, you have current. And then also notice that the positives and negatives would go in opposite directions. You may not always have positive and negative. You might have only positives, or you might have only negatives. And most of the time for us, we're dealing with metal wires, and they have negatives. So this is really more of our scenario, okay? Now, I thought it would help then to give you an analogy. Here is my little aquarium. This little aquarium then has an energy source, that pump down there. If I turn the pump on, right, it pushes the water molecules. And that is the current, right? The water molecules that are flowing. Okay? And that's the mental picture I want you to have here is you would have the same thing happening here. If I come over to here and I take my power supply, guess we're kind of done with this, and I turn it on and give myself about 6 volts or so. Okay. And I come over here and I hook 2 wires. Oh, with a switch. Yay. Okay. And so I hook the switch and I hook up a wire and give them a path that they can flow through. What happens when I close the switch?
Nothing.
Nothing. Okay, no switch. All right, here's my switch. All right, so then the light goes on here, right? And so this light is kind of an indication of, hey, electrons are flowing. As they are flowing through, they are giving up their electrical energy. Right here, this is their loss of energy. There's 6 volts that they're giving up. They came from here with a lot of energy. They lose it somewhere along the line, and that's what they're losing it. They're giving up that electrical energy and in a process making light and heat. Probably more heat than light, but nonetheless, the total still adds up to that conservation of energy. And so that's my little circuit here. And if I could get down on a microscopic scale, I wouldn't see this, or this scenario. I'd be seeing this scenario. All of these could exist, by the way, but it's that last one that is the simplest, is the electrons come through here and they go through that little filament, and there's the key, that little tiny filament. That's what I was trying to draw right here. Okay? And now they just keep going around. They keep going around. They keep going around. And I would say then there is some current in here. And that's what I was trying to say. Because you can't see these electrons moving, it's nice to do this for the students and say, look, you see those water molecules moving? In fact, you don't actually see the individual molecules, do you? Which brings me then to the units for measuring charge, as well as the definition of current. And so here's what we're going to do. We are not going to say how many billions and billions of electrons flow every second. We're going to change that. We're going to say the definition of current is how much charge flows in a given amount of time. Now again, if this helps, don't we do that with water? If I were to turn this on, you might say, hey, this is flowing at about 50 milliliters a second. I don't say 6 billion molecules flow every second. I say 50 milliliters. And I don't know how many molecules, by the way. I'm just making that number up. Okay, are in there. But we don't really count the number of molecules. We count the volume of water. Fair enough? And so the same thing here. I want you to have the fundamental physics concept. The fundamental physics concept is the current really is the flowing of charges. There are individual charges that are flowing, and there's lots of them. But instead of saying how many individual electrons flow, we will say how much charge flows per time. Which brings me to the units. What would this tell you in terms of units? Yeah, how many coulombs per second, right? And just as a little side note, how many electrons again does it take to make 1 coulomb? That's the 6 billion. That's what I was thinking when I was talking about the water. So if I really did have a picture like this, and right here I had 6 billion electrons flow every second, that would be 1 coulomb every second. And we give it a name. I think you know it, some of you do. What do we call this? Yeah, we call it an amp, symbol A. Okay? So again, mental picture. What's flowing? Charges. And if you have 6 billion electrons flowing, that's 1 coulomb every second. And that would be 1 amp. So 1 amp means just that. 6 billion electrons are flowing every second. Okay? And that's the conceptual picture that I want you to have. Also, look closely at the map. This was your question. If you look closely at this, this is saying what? How does the charge change? Not the number of particles. Let me go back to the first picture, but I'm going to leave that one on here. Didn't that first picture look like this? It had a positive charge flowing across the surface like that, right? Let's just say, for the sake of discussion, that this side of the wire is neutral and this side of the wire is neutral to begin with. So I'll say it has 0 charge, 0 charge. When this one positive charge moves over to here, what do we have over here now? Isn't this now a negative 1? It depends how much charge is here. Let's just say it has a charge of +1. Isn't this now negative 1? And what's this one? Positive 1. Okay? And so what you would say is, when you looked at the charge flow, wouldn't you say 1 positive charge went from there to there? It kind of makes sense. 1 little particle went from there to there. Fair enough? So you would say, which is the direction of the movement of the particle? Well, doesn't the particle move that way? And doesn't the charge change that way? Don't we go from negative to positive? Now the reason I say all that is, what if this picture changed? What if this was an electron or some kind of negative charge? And to keep it simple, I'll just say it's -1. And let's say that -1 moved across here. And again, let's just say both sides were neutral again. Oh, maybe I should do it this way. Let's say the negative moves that way. How about that? Not sure which is better to explain it. But this might lead closer to what I'm after. If you had neutral and a negative move that way, what would be the charge over here now? +1, right? And what would be the charge over here? -1. And what I really want you to see is, can you see that the change in charge in each scenario is the same? The flow of current is not defined by what direction do the particles flow. Did you catch that? I'll say it again. The definition of current is not necessarily the direction the particles flow. That is not the definition. The definition of current is the direction that the charges flow. Fair enough? So if it's a positive charge, then the direction the particle actually moves is also the same direction that the charge flows, right? So current would be in the same direction that positives flow. If I come over to here and I look at these 4 positives flowing to the left, which way is the current? To the left. But this one is easy to overlook. When a negative particle actually moves to the left, which way is the change in charge? To the right. Do you see how the change in charge, because it has a negative charge, is opposite to the direction it flows? Do you see that in the math? And I'm hoping this picture helps, because when I come over here and I say the electrons go that way, what direction is the current? That way. So when I hold up this little power supply and this light bulb, and I say the electrons are going this way, what direction is the current? This way. Now, are there any positives going this way? But is the current this way? Okay? And that's easy to overlook. The direction of the current is defined not as the direction the particles flow. Did I say that? Should I say it again? The direction of the current is not the direction that the particles flow. It is defined as the direction that the charge changes. And that's why when we have positives that go this way, I think mentally it's easier to see. Mentally, you see, hey, positives are actually going that way. And so does charge. But I think mentally this one's a little harder to see. When the particles actually go this way, there's a buildup of charge that way. And the buildup of charge is what we're going to care about. We don't really care whether they are positive or whether they are negatives that are moving. We care which way did the charge increase by. So that's going to be our focus, which hopefully then somewhat answered your question. Okay, you have another one. But that's why I keep saying electrons go this way. But after we take the test and we start getting more into these chapters, I'll say the current's going this way. Because that is the direction of the current. But yet nothing is actually moving that way. Unless we have a more complicated scenario like A and C.
So there's nothing natural about the electron that makes it negative. We just call it negative.
Right. You might.
Why didn't they just call the electron positive so it would be the same direction as the current?
Well, everything's beautiful in hindsight, right? It all comes down to Ben Franklin. He didn't know which ones were moving. He was smart enough to realize this scenario that it didn't matter. He didn't know if we had both moving or just positives or just negatives. But he did know that if you give this some thought, the flow of charge is the same either way. So he just goes, well, let's just assume the positives are going, and that's great, and that'll give us, and if later on we find out it's the negatives, which we did, then so what? The current will just be opposite to the direction the electrons are moving. Okay? But I do want to emphasize, it's dq dt. It is not dv. You know, the direction of the velocity. It's not a change in their velocity. It's not where did they go, or change in their position, a dx. That's not what this is. This is a dq. And because of that negative, it can leave us with an unfortunate, annoying problem of the electrons go this way, but the positives go that way.
That's the good thing about science is that when we find out something's wrong, we can change it. Right?
What about chemistry? Aren't there positive charges we can move there?
Okay, well, and then that's what I'm building up to. So even if you made this extra effort to switch it, it doesn't completely help you, because look at this scenario. What if I had a situation where both positives and negatives are moving? Now, I do not have that situation in a wire, but in a liquid I do. When I take a battery, a water-filled battery, I have the positive ions and the negative ions that are in that reaction. Okay? And so if I look closely at what's going inside of a liquid, I will see that the negatives are going this way, the positives are going this way. That's what this is trying to say. What direction is the current, though? Isn't the current that way? Regardless of whether the positives or negatives are moving. And this is a scenario where I actually have both. Okay? So the point is, you wouldn't want to switch it and change it, because it would only be good for a wire now. It's not going to help you when you have both of them. It's also not going to help you when you have just positives, which could happen like in a plasma or the equivalent of what we call holes in silicon. And so the silicon has, for lack of deeper explanation, has positives that are moving. So I do have scenarios like this. And scenarios like this, you would be very happy that the direction they move is the direction of the current, right? You're kind of unhappy with this scenario, but you're never going to solve all of it. So that's why we just live with it and say, look, this is no point in changing it. This is the definition. All right. Now this is a long way of really me trying to head off a problem that I've seen students come across in past years. They get all frustrated between not understanding what current is versus the movement of those electrons. But I hope this really helped by pointing out this is our definition of current, how the charges change. So a positive going this way is exactly the same as a negative going that way. It's not the direction that the particles move, it's the direction that the charges change. All right, well, with all that said, maybe I'll do a quick step in terms of math. Not much, so, because like I said, I don't want to do too much math here, but I think you're getting a good picture then of what's going on. And in picture number 2, your author does this for a moment. He says, let's take a microscopic view, okay, of a wire. And so here I think he does a little better job in his picture by saying, I'm going to take this wire, and I'm going to show the whole wire. And he does something like this. He said, okay, imagine cutting this. So this is the cross-sectional area right here. And he said, let's look at these charges. And he has them as charge Q. Just for the sake of discussion, let's say they're positive. And that means the current would be going that way. Now, if they were negative, of course, the current would be the other way. All right. But here they are moving along with a velocity, v sub d. We're going to call that the drift velocity. More on that in just a second here. But let's look at this for a second. Wouldn't in a small amount of time these objects move a distance of v dt, right? They would move a distance of delta x. And so here's what your author is trying to say. If you got down and you looked on a microscopic level, and you take this wire, and you look at a small piece of it, some distance delta x, and you watch the charges that are moving over a short period of time, and you ask yourself, how much charge would go through here? Wouldn't all the charges that are in here move during that delta time? Okay? So if I ask myself, what would the current be? I would take, well, how much charge moves through in a given amount of time? Okay. Well, let's break that apart here. Let's break that apart to 2 factors. The first one, I'll say, how many charges went through? And I will multiply that by the charge on each particle. Right? So again, in this picture, they're showing 2. So if I wanted to know how much charge went through here, it would be the number of particles, so there's 2, right, multiplied by the charge of each particle. Fair enough? In fact, let's take one more step that's going to become very useful in our electronics, as you'll see here in just a few weeks, is the number of charges. Let's do this. How about we write this as the number of charges per volume times how much volume do I have. Then multiply it by the charge per particle over delta T. Now again, you might be wondering why, but now maybe you can see it. What's this? The number of charges per particle. Isn't that going to be related to the density? If I grab a piece of copper wire, right? And I know that in a piece of copper wire that one electron comes off. If I know how many atoms per volume, don't I know how many electrons per volume? And that's going to be the neat part about it. I can get this number. That number is not too hard to get. In fact, we're going to give a symbol for it that we're going to use a lot, and that is N. And so after the test and we start doing some more numbers, you're going to see that show up a lot. How many charges do we have in a given volume? Right? Like I said, if this is copper, we're usually saying that we get one electron for every atom. So if we can just look up the density of copper, we can then find out how many charges we have per volume. Now, the other part of this, the volume, would be the speed that they're traveling, the time it takes times the cross-sectional area, right? That's this whole volume as it moves across. And the charge per particle, well, that's what we meant by that symbol Q up there, right? That's what we say all the time. We say, look, Q. All right. So maybe I'll circle that one also. But you've already been acquainted with that. So what's new here, of course, is this symbol N. How many charges do you have per volume? Volume, you already know. Charge per particle, you already know. But your author says, since you're trying to find current, current is divided by time, and you see something very useful in our first step towards understanding our electronics, and in this case trying to understand current, is current then would be related to these four factors. And so sometimes we're going to look at what is the overall current, and other times we're going to look at why is there an overall current. What factors go into play that determine the current? And you can see there are four of them, right? It is saying, look, how fast are they traveling? How much area do you have? How much charge do you have per particle? And how much particles do you have per volume? You put all those together. And so as these electrons go through, this is what we might call the microscopic view. We'd be looking at individual charges moving at some speed in a cross-sectional area, their concentration. You put them all together and we might have what we call the macroscopic view. We put them together and we just say, look, what is the current in here? It's 1 amp. And if we wanted to go back to the microscopic view, we would say, well, that is 6 billion electrons every second. How are those electrons spread out? Well, they are spread out over a certain area. They're going at a certain speed, right? There's that concentration of them. And so maybe I'll put a little box around here kind of as our first equation and say, look, this is the idea of current. Well, the second thing then I wanted to get across to you then is that little pinch in the wire I was talking about. How come they didn't want to all go rushing through?
When you say number of charges, you mean number of particles?
Wait, number of what?
You said number of charges, do you mean number of particles?
Well, yeah, I guess I mean number, yes, I do need number of particles with charge. Yeah. Yeah. I guess that's what I mean. It's the number of particles, but only the particles that have charge that are moving along, because I can have like the nucleus that's not moving, and I can have core electrons that are.
Number of charged particles.
Yeah. Number of charged particles.
Oh, don't you want charge density? Small n, not too east, that's about big N.
No, I don't want charge. Charge is going to come here, right? So this is the number of particles in the volume. Times the volume, that's the number of particles. Then when I multiply by charge, that's how much charge I get.
Yeah.
Yeah.
So small n is the number density, not the total number of charges.
Oh, right. So little n is the number of particles with charge in a given volume. Yeah, it's so, that whole thing. This is a density per volume. Because then I multiply by volume to get the total number of charges. Then I multiply by the charges when I have to get the total charge. Yeah.
But you said n is charge density?
So n is, it's not charge density, it's particle density. Little n is particle density. Well, again, and I apologize. I didn't want to spend too much time necessarily doing that map, but I saw the opportunity and I said, okay, let's throw that out there. But I think that gives us a better understanding of our first step. What is current? And really all that I want to get across here in this first step is it's these moving charges, okay? And most important after that is this definition that when a positive goes this way, it's the same as a negative going that way. That's an important concept here. Because the other side of this is resistance here. What is stopping them from going through? That's what we mean by this resistance. If I came back over here to this pump like this, and I said, okay, I'm going to turn on this pump. Okay? And so we saw this earlier where I turn on the pump is pushing the water molecules, okay? They're going through here. The number of water molecules are flowing. That's the current, right? What if I were to pinch it with my fingers a little bit? Maybe like that. Do I still have current flowing? But I have less, don't I? Why? Because I have something stopping it. I have a resistance, right? So the resistance really is a measurement of how come more don't want to flow. What is stopping it from flowing? And maybe I should add to this as we kind of get into Ohm's law. What's pushing this? Isn't it this pump, this voltage? And so notice I can change the amount that flows by changing the resistance, right? Now, of course, I think in this one you can kind of see why there is a resistance. That's easier to see. Then I think this one. Why is there a resistance here? Yeah, I drew the picture earlier, but if I were to take this wire and give it some thickness here, and then somewhere in this wire I make it kind of narrow, as I was trying to say, aren't I trying to pinch all those electrons in there? And that is going to then bump into each other, if you will. Now, not that they really hit each other, but they make an electric field. They push each other. They push the next one back from coming. And so that's what I was trying to draw earlier when I said these electrons build up here, and they do keep squeaking by there. But if that wire was wider, do you think that they would get through a little bit better? Yeah. And so that is your resistance. And so just like the size of the rubber tubing there would depend on how much room they have to get through there, the same thing happens for this filament. I don't know if you noticed, but this wire here has a pretty thick diameter. Now it's hard to tell with the insulator on there, but that diameter's probably got to be a millimeter or two thick. Fair enough? You ever look real closely at a light bulb? And there is a very, very, very thin wire across there. That's what I'm trying to do. I'm trying to shove all the electrons that are going through here into here. And so what happens? Yeah, they get some resistance. They can't get through there. And so that's why it's not like an infinite number going through here. But this guy tries to push them through, and then this tries to stop it. I like to hold this up if this helps. This is kind of our simplified model of a wire. So here's my wire. Okay? Here might be a better picture of a microscopic view of what's going on. I'll start with this one and say, okay, here's my wire. Here is my electron in the wire. These little nails represent the atoms here. So let's say this is just copper. And so they're kind of moving around, bumping in, hitting an atom or two. But there's nothing pushing this electron yet, one way or the other. And that's what this picture is going to be. It says, look, you start with an electron maybe right about here. It moves out. Oops. Here. It moves out, it hits an atom, bounces off of it, hits another atom, comes over here, hits another atom, comes over here, hits another, and maybe ends up about here. This one here looks like it bounced off, bounced off, bounced off, bounced off, bounced off, bounced off, and that one kind of ends up back where it started. In other words, is there any net movement to this? No. Is there movement to it? All right, so I want to make sure I get this clear here, because it really comes back to this drift velocity. I'm not talking about the speed that these guys are moving, because they are actually moving very fast, many millions of meters a second as they ricochet around. But they essentially just go back to their same spot, unless what? Unless you push them. So in our make-believe model, what if I did this? Doesn't this have a tendency to push the electrons this way? Right? And so every time they ricochet off, they would rather go this way than that way. And so as they bounce around, they look more like this picture. That here's this electron, and it bounces to here, and bounces to here, and bounces, and bounces, and bounces, and bounces. And so is it still moving very quick at millions of meters a second? Yes. But as it ricochets around, it takes a long time to drift. Do you see the difference? Which speed am I interested in as far as the flow of current? Am I interested in the speed of the electron? No. I'm interested in what? The drifting speed. How does this bouncing electron make its way down to the end? And so this little model doesn't show everything quite well, but it does show really well electrons trying to get through a wire. They will drift as they go along. Oh, that's a bad example. You try some smaller ones. Maybe they won't get as stuck. But do you see how they have a hard time getting through? Because what are they doing? Aren't they hitting the atoms here? See, and that's what I'm trying to say here. These guys are trying to get through. They get affected by a lot of different factors. We're going to talk about 4 of them, and it looks like I'll run out of time to mention all 4 of them. But there is some resistance. Guess what we will call it? R, and say, look, how much resistance? And maybe I should just rattle them off real quick and then come back to them after the test here. But if you look closely at this, can you kind of see why the electrons can't get through? Do you see how they were crowding into each other? Wouldn't that have to do with the width of this wire? And so what we're going to see here is the size of this wire is one factor in terms of the resistance. That's the one I was showing you. I was showing me pinch the wire off and making it harder to get through. That's what I was trying to say with this light bulb. That if this wire is narrow, they crowd into each other, they push on each other, they bump into each other, it gets crowded. That's one reason for resistance. Do you see the other 3? How about how long it is? Would you agree if this was longer? they would be bumping into each other more often and more likely, and they would hit more atoms along the way. So wouldn't the length of the wire matter? And so we'll talk about that one. Number two, do you see it's just the material itself? Do you see that they're hitting the atoms? Do you think there'd be a difference if this was made out of aluminum atoms versus copper atoms? Yeah. And then finally, the last one I think is the hardest one to see of all. But you guys saw it in the lab really well. If these are the atoms, in this little picture I have here, they're kind of stationary. Is that really what's happening to the atoms? What are they doing? Aren't they vibrating based on their temperature? So what would happen if I warmed this up? Wouldn't they vibrate more? It would be like this atom's taking up more space. Wouldn't it be harder for these little electrons to get through? And so when we come back after the test next Thursday, I'll pick up there and say, do you see all four reasons why there is a resistance? Do you see it has to do with the size of the wire, the length of the wire, what it's made out of, and how much the atoms are moving? All four of those. All right, well, we'll leave it at that. You got a lot of work to do this weekend, so we'll focus on that.